Okay, so yeah, maybe let's start. So what we were doing last time was, sorry, yeah. So the idea is pretty much before we finish continuous functions, I want to say something else. So last time, kind of what we did was, well, continuous maps, and for the last part of the lecture, I focused on this. So the continuous map will look something like f from x to y, and I introduced restriction to some subspace, and then we also discussed co-restriction to some subspace of the codomain. And then we introduced very briefly these homeomorphisms. So these are supposed to be continuous bijective maps. With continuous inverse. And I was trying to focus on how this continuous inverse is not for free, as was the case, for example, in linear algebra. So if you have a bijective linear map, then the inverse will be linear. Not the case here. So this is something that we should try to understand better. When is the inverse continuous? And a very naive way of doing that is, let's take our first definition for today. Let's take two topological spaces. Let's say x and y. And we're going to say they're homeomorphic if we can find some homeomorphism. If there exists homeomorphism. From x to y. So of course the question is, where do we have such thing? Of course, not always the case, and very nice tool to have, mostly vocabulary. So let's call this a proposition. Suppose we have a bijective map x to y. So between some topological spaces. So in principle, we are not saying f is continuous. What I want to understand now is when is the inverse going to be continuous. So then the inverse map, f inverse from y to x, is continuous if and only if fu is an open subset of y whenever u is open in x. So for all u inside of x open. So I'm talking about continuity of the inverse here. And you can just measure that using open sets in X. So the proof for this is going to be on the next homework assignment. So in other words, what you should try to do is, if you want to show f inverse is continuous, you need to compute pre-image under f inverse of some open set in X. So the idea is this, of course, is just going to be f of u. But that's something we need to prove. So these two inverses mean different things. This is the inverse function. This is the pre-image of this function, of this set under this, of this set under this function. So in other words, this is telling you if you want to show the inverse of a function is continuous, you only need to verify something about the function itself. So of course, this is something that will have a name on. So that's the next definition. So function, or this function, let's say, f from x to y is open if, well, exactly this. If f of u is open in y, whenever u is open in x, for all open sets in x. So this is what I'm defining here, this notion of being open. And why do I want to emphasize this? Mostly because I want to introduce an interesting example. So maybe let's start with some not so complicated examples. So the first one is, let's try to illustrate this notion of homeomorphic spaces first. So two spaces are homomorphic is if there is a homomorphism. And eventually you should get convinced that two topological spaces are homeomorphic if they are the same. And that's pretty much by definition. So topologically, they should be the same. So let's take this function given by, I want linear map. F of x is going to be ax plus b. But I want this function to be invertible. So let's say a is non-zero. Then this map is continuous. This is something that you should know from analysis. And also, of course, bijective. So the inverse here can be given explicitly. The inverse, let's denote it by F inverse from reals to reals. It's given by, well, F inverse. So if you're here, if that's going to be Y, then this should be, F inverse should be Y minus B over A. So that's why you need your A to be non-zero. Of course, this is also continuous. Continuous. So this F is homeomorphism. Homeomorphism. Are there any questions so far? Okay, so let's maybe do something maybe more surprising. Let's take the open interval. Maybe I should say this subspace -1, 1 inside the reals. So here with the subspace topology. Induced topology. So this is from Hamburg 1. We also recall what this was last class. So let's take this function. This function, let's call it G, from reals to reals. In principle, let's say G of x is going to be this normalized version of x. So x divided by 1 plus absolute value of x. What we're doing here is kind of normalizing x. And as a consequence, this will always take values, not on the entire real line, but the image of this will be the open interval. So G of R is just the open interval. So by our theorem from last time, the last theorem, since G is continuous, its co-restriction is continuous. We will have a continuous map. By co-restricting, this is what we know the G to the -1, 1. It's a map going from the reals to our open interval, which is also bijective, which is pretty easy to show. So here we have a continuous bijective map from the reals to this open interval. Okay, that's interesting. What about the inverse? The inverse of this map is, let's call it H, going to from the open interval to the reals is given by H of, let's call it Y, is going to be, in this case, Y divided by 1 minus absolute value. So it's very important that we're restricted to this interval, because otherwise we could have like trouble here with this denominator. But this function is also continuous, which you can prove using your usual analysis knowledge. So it's a quotient of two continuous functions where the denominator is never 0. Okay. In other words, we have just proven that the reals are homeomorphic, or the space is homeomorphic to this open interval -1, 1. So what this means is, topologically, the entire real line is the same as just the open interval. And what we're doing with this map, maybe let's stay with this map, is we're just contracting the real line. And what we're doing with this one is we're kind of expanding the open interval to the entire real line. Are there any questions? So of course, now that you know that, of course, this open interval is also going to be homeomorphic to any other open interval. That's also going to be a homework assignment. I won't even write it here. But open intervals, they are all the same, regardless of whether they are infinite in both sides, just one of the extremes, or none of them. Any questions? Okay, third example. Here I will start with this function. So maybe let me first introduce the spaces I want to study now. So S1, this is going to be points in R2 where x squared plus y squared is 1. So this is the unit circle. Of here, this is a subspace of R2, so we consider this with the induced topology. Which means open here are going to be opens in R2 intersecting intersection with S1. I will write that in a second. So the idea here is I have this function. We have the function f from, let's say, going from all the reals to R2, given by f of t, let's call this, is going to be cosine. Instead of doing t, I will do 2 pi t, sine of 2 pi t. So what this function is doing is not something new. It's something like, here's the unit circle. And what the function is doing, you're starting from here, and you're going around the circle. And after, say, from 0 to 1, you're already here. And then you start doing that again, and then again, and then again. So what this function is doing, it's going across the circle counterclockwise infinitely many times. What we can fix that, instead of considering this function, which, by the way, which is continuous. So which is continuous, that's very important. Let me write that. So the function is continuous. Why is that the case? Because it's a function going into a Cartesian product, and we proved that last time. such a function is continuous precisely when the two coordinate functions are continuous. Because, so let's write down the coordinates f1 going from reals to reals. Here, p goes to cosine of 2 pi t, and f2, where t goes to sine of 2 pi t. So I'm just taking these two coordinates. These are both continuous. And again, that's a classical analysis result. So this function is continuous. It's absolutely surjective, right? Everything in the unit circle looks like that. But we're just going around the circle infinitely many times. So to fix that, we can just restrict and co-restrict. So let's say this function induces by restriction and co-restriction. We'll get a continuous map. Well, let's call it maybe G from 0, 1, close at 0, open at 1, to S1, just given by F. So G of t is just F of t, which means cosine of 2 pi t, sine of 2 pi t. But the thing now is, since we're restricting to 0, 1, the function is going to be injective because you cannot get same values for cosine and sine with two different values of t here. And it's still surjective. So this continuous map is also bijective. So what we're doing here is going back to our circle picture, something like, here's the unit circle. Here's the unit circle. And what this function is doing, at 0, you start here. You start going counterclockwise. Here, maybe I can say what time, here where time equals 0, at time equals 1/4, times equal 1/2, oops. Let's do that again. Times equals 1/4, we're here. Times equal 1/2, we're here. 3/4. And at 1, you're getting to the origin, but you never reach it. So this function is injective because we are close at 0, open at 1. And it's surjective. That's great. That means we have an inverse function. The inverse function, let's call it h. Let's call it h. Now, the thing about this h is it's not going to be continuous. And now I'm going to use the notion of open I just defined. So this is a very interesting example of a bijective continuous function that's not a homomorphism. So why is the inverse not continuous? Maybe I don't want to use H inverse. Let's just stay with G inverse. So to show it's not continuous using our lemma, it's enough to show that this G is not open. Yeah, I see there's a question. You can just unmute yourself.
I do, but actually I want to continue before asking the question.
Okay, so I want to show this G inverse is not continuous. In principle, I need to do like pre-image, blah, blah, blah. But our lemma, let me go up. Our proposition is how I called it. The inverse map is continuous if and only if the map itself is open, which means every open in the domain should go to an open of the codomain. So instead of proving that the inverse is not continuous, I can just prove that this map is not open. Oops, that this map is not open. So to show that, it's enough to find some open U inside our domain, which is 0, 1, for which the image G of that U, which is a subset of S1, is not open within this topology. So that's all we need to do. And the idea here is going to be kind of looking at this again, not that complicated. So the idea is, let's take, again, our unit circle. Our function is doing this, starting from 0 here, at time equals 0. You start traveling through the circle. And at time 1, you're at the beginning. But if you stop before getting there, so suppose you get to this point, something like this. How do you get there? Just using the first 1/4 of your interval. So let's take that U. Let's take that U to be 0, 1/4. And this is open in our domain. For example, it's 0, 1 intersecting -1/4, +1/4. So it's open. But this is what you get when you do G of U. So this is our G of U. G of U is here. Maybe I can put like that, pictures. So picture, we have 0, we have 1. And when you do that, you get the entire circle. But if you restrict to 0, 1/4, you just land here. But closed at this point and open here. And well, opens in S1, we need to look at open sets in R2. Remember, these are unions of squares or rectangles like this, because we're considering the product topology. Now, when you intersect that with S1, something like this, you're getting just open here, open here. There's no way for us to get close it here. So this is not possible. So I will not say exactly why now, but this is never going to be open in S21. This is something we need to prove later. G of U, which is the point of the form x, y in S1. And the restriction here is x is bigger than 0, y is bigger than or equal to 0. So that's how you express these guys. This is not open. And the idea why this is true, it's true because 0, 1, the point 0, 1, sorry, 1, 0 is an element of G of U, but G of U is not a neighborhood. It's not a neighborhood. Because the moment you want to expand it, you need to go out of it. And this needs to be proven. But from the picture, it's clear. From the picture, it's clear. If you consider an open set, you're going to go beyond the open line. Any questions?
Yes, I do have one question. So just to clarify, could the same also be said about the point 0, 1? Like if you took an interval from 1/8 to 3/8, that
absolutely.
That also would.
So sorry, you said 0, 1.
Yeah,
but I'm
so
not so sure.
in
Zero
R2,
should-
0, 1, let's say we take the interval from 1/8 to 3/8, t is from 1/8, yeah, that point. So that
Correct.
also would not be open.
But in that case, so what the open, you're saying you want to go from 3/8?
1/8 to 3/8, let's say. So basically
So
the top.
something like from here
Yes,
to here.
yes.
Well, but in that case, you need to take open and open, right?
Oh, okay, I see.
So here we're really using that we're starting from 0 here with our domain.
Okay,
I really need this one.
I
Yeah.
see. Okay, thank you.
Yeah. So yeah, this is not a neighborhood of 1, 0. It's not hard to show. It's like because in S1, let's say, because neighborhoods of 0, 1, of 1, 0, sorry. No, it's okay, it's 0, 1. No, that's right. My point is 1, 0. Neighborhoods of 1, 0, sorry, contain always points with negative second coordinates. Second coordinates. Because they always contain something like 1 minus epsilon, 1 plus epsilon, or let's call it epsilon 1 times 0 minus epsilon 2 times, comma, 0 plus epsilon 2. So you're always going to have something with negative values of y. And that's not the case in G of U. So these guys, not all. So this is a very interesting example of a bijective continuous map for which the inverse is not continuous. So at this point, we cannot say that 0, 1 is not homeomorphic to S1. We just proved that this map is not a homeomorphism. But to be honest, we shouldn't expect these two things to be the same topologically. We're not ready to prove that yet, but these two things should be different topologically. One is kind of a segment of a line, and the other one is a circle. So this should be different. And we will develop the tools that we need to prove that no map can be a homeomorphism. We'll prove that at that point. No map can be homeomorphism. It could be closed, like this one. It's close to homeomorphism. This is a continuous bijective map, but the inverse is not continuous. And we'll prove that this in the future. Any other questions?
One last question. Is it because
Yep.
there is some principle that allows us to say a circle is fully connected at 1, 0? Is that why?
Yeah, but also 0, 1 is connected or fully connected, if that makes any sense at any point. So what you're saying is okay, but the reason is more complicated.
Okay.
So first of all, we'll need to be very careful with what we mean with two things being, or with one thing being connected, with topological space being connected. I mean, from the pictures, it's very clear what that means. And then we'll need to introduce a notion there. And if you look at that, these two things, they are both connected, whatever that means. And the trick here will be, it's easier to make this guy not connected than this guy not connected. That's pretty much what will happen. Here, if you delete any point, not being the first one, not in the left extreme, you delete any point, then you will lose connectedness. But here, if you just delete one point, you will still be connected. And that's kind of what's behind this. But we don't have the tools. We don't even know what these things mean. We don't have an idea. Any other questions? Okay, so that's all I want to say about homeomorphisms for the moment. Now I want to switch to a very interesting topic, metric spaces. So this is mostly based on sections 20 and 21 in Macros. So the idea with metric spaces is maybe not necessarily the idea, but we want to exploit this crucial fact or crucial idea what we use for the reals. So how did we introduce the standard topology for the reals? Well, we use these open balls. So ball center of A, radius, let's call it epsilon, which is by definition all real points, which are a distance at most epsilon from A. So we use these balls to define the standard topology. And the crucial thing is that we have this notion of distance. So this should be distance from A to X. And that's all we need. So let me say we have a distance function. On the reals, maybe on R, we have a distance function. Namely, if you give me 2 points, I know how to compute in some sense its distance. And what we want to do now is, well, we want to generalize this idea to any other instance in which we have a distance function. So what I'm going to do next is I'm going to write what should be the axioms satisfied by a distance function. So this is definition 4 for today. Here we start with just a set. There's no topology at this point. Let's start with a set. And I'm going to define what's a metric on X. A metric, also called distance, on X is going to be a function. So if I'm going to compute distance between 2 points, well, I need a function with 2 variables. So let's call it d from x times x to, well, distance should be positive numbers. Could also be 0. So this is a natural codomain space for a distance function. But now we want this to have some properties. And we want 3 properties. The first one is, maybe let's start saying for any x, y, and z points in our set X, the first property is if you have 2 points which are at distance 0, well, that should only happen when these 2 points are the same. So distance from X to Y is 0 if and only if X is Y. That's something that should happen. We don't want 2 different points to be at distance 0 from each other. So this is what's called non-degeneracy of the distance function. So I don't know what this function is, but I want it to have these properties. Second one is computing the distance from X to Y should be the same as computing the distance from Y to X. And function satisfying this, it's called symmetric. That also makes sense. Shouldn't matter where you compute the distance from. And the third one, I mean, everything here is important, but this one is really what's behind everything. If you want to compute the distance from X to C, well, what you should have in mind here is you have something like, this is your set, here X, here's your point in C. Now, in case you have a third point, it should always be easier to go from X to C instead of going first to some other Y and then to C. So how do you write that? Distance from X to C should be smaller than or equal to the distance from X to Y plus the distance from Y to Z. And this is called the triangle inequality. Any questions? So this is just the definition. These are the minimum things that so this is what I'm defining. This is called a metric or a distance. Now these are the three properties I wanted to satisfy. Any questions? So this section is called metric spaces. I'm just defining what a metric is, but of course, a metric space is now just a set with a metric. So it's a pair. So this is still part of our definition, x comma d, where d is a metric on x, metric or distance on x. And remember, the important idea here is supposed to be this idea of balls, and we can define that. So if we have still part of our definition, if xd is a metric space, then we can denote, maybe let's, for any point, let's call it a in x, and any epsilon positive, we can define our ball, which depends on d of center a and radius epsilon to be all points in our metric space, which are a distance from a at most epsilon. And this is called open ball. Here, open is just formal for the moment. Open ball centered at a of radius epsilon. So it's a subset of x. And I should say, we usually don't write d if it's clear. Don't make it explicit if it's clear. Usually. You only write the d if you want to distinguish different metrics on the same set. Any questions? Okay, examples. Of course, we're going to start with the example that we're basing everything on here. So example 1 should maybe be called example 0 is you start with the x to be the reals with the distance, the usual distance from x to y is absolute value of x minus y. So this is going to be a metric space. That's the usual one. Now, a more general version of this is now you can take r to the n, and you can consider what's called the Euclidean metric or distance. So the distance from x to y in r to the n, points are tuples. So the distance, let me call this d2. I will explain that in a second. It's, you take the sum from 1 to n, you do xi minus yi, you do squares, that's why you have a 2, and then you do square roots. This is called the standard Euclidean metric on Rn, but more generally, this d2, this standard metric, you can generalize it to any p in which is at least 1. So for any p bigger than or equal to 1, we can define a metric. So probably you haven't seen this one before, dpxy. So very similar, but instead of 2, I will use p xi minus yi squared, sorry, p, pth power, pth square root. Sometimes this is called the pth metric, but that's not very standard. And now we're claiming these are metrics, so there are some properties we need to check. The first two are kind of clear. That's not really a problem. What needs to be more carefully analyzed here is the triangle inequality. That one is not for free. So for the triangle inequality, let's say I will not prove it, but it's usually if you want to oops, sorry, there's typo here. If you want to see why the triangle inequality is true, I don't expect you to prove this, but I mean, in the case p equals 2, that's something you should know how to prove. But in this p case, this follows from something called the Minkowski's inequality. That's an analysis results. But we don't need to focus too much on why that's true. I'm just telling you triangle inequality works here, and this is the reason why it works. Okay, so now we have several different metrics on the same set X. At some point, we need to address that, but it's very interesting to have this. For each P here, we have a different metric, so a very large family of metrics. Let's make this even worse. Let's have an extra example. Maybe we want to include infinite here. So this is kind of what happens when you let P go to infinite. So for P equals infinite, we have this metric. Also on Rn, distance P between X and Y. Here we just need to compute the max of the absolute values here, xy minus yy, for all coordinates. So you compute coordinate-wise the distance, and then you just take the maximum distance between two different coordinates. And this is exactly what you get where you let P go to infinite here. And this is a typo. Shouldn't be P, should be infinite. Sometimes called the infinite distance or norm. Okay, we have a bunch of examples on Rn. Now let's go back to a general set. For any set X, we can always impose a metric here. So to be honest, X needs to be non-empty, but that should be included in the definition. We can define the somehow a trivial distance, but let's call it discrete. And we know this word means something for us. So the discrete metric, which is given by the distance from X to Y, it's going to be, well, if the points are the same, it should be 0. We know that. And otherwise, let's just say it's 1. So this is distance just taking 2 values. So it's not very good as a distance because you can just decide if 2 points are the same or not. But it's always a metric. Okay. So far, there's no topology going on here. Are there any questions about these definitions and examples?
I believe there was one question in the chat. If
Oh,
we
sorry.
are allowed to use Minkowski's inequality.
Oh,
during
yeah. You're allowed to use it. To be honest, you can just use that this dp is symmetric, and that's all you'll need. And to be honest, we will not be computing too many things, but I don't really expect you to use it. So don't worry about that. Just need to know that triangle inequalities for NDP. Okay. Proposition, because we need to make this topological. It's proposition 5 for today. Of course, I'm going to start with a metric space. And I want to impose a topology here. And the idea will be, well, exactly what we did for the reals, for the standard topology on the reals. You have a metric space, and the claim here is that the collection of open balls So what's the collection of open balls? Let's call it B. Math BBB. So it is all. I'm using A, where A is any point in X and epsilon is any positive number. Notice I'm not using BD here, but I should in principle. It's going to be a basis for some topology. That's our proposition for a topology on X. Of course, we need to prove this. And definition, so previous thing should be called proposition / definition, but the definition here is that topology, so the topology generated by B, which we denoted before by T of B, I'm also denoted now by T sub D because it depends on the distance. It's called the metric topology on X. Or also called sometimes the topology induced by D. Okay, so of course we need to prove something. We have this proposition over here. We need to prove that this, so this is what we want to prove. That collection is a basis for some topology. We don't have a topology on X. We're claiming it's a basis for something. So before proving that, let me state this lemma. So this is something that we were playing with before without proof for the reals, because it just makes sense over there. So the lemma is the following. Let's take any open ball. Let's call it Bx epsilon in B. And now let's take any element in that ball. So let's say for any y in the ball. Well, the important thing about balls is they should be open, right? That means they should be a neighborhood of every point in the set. So if you take any point there, there should have a neighborhood, and that means there should have a ball. So for any y, there exists some positive delta for which the ball centered at y of radius delta now is inside of the ball center x radius epsilon. So kind of what's going on here, the proof for this is, let's try to make drawing. Should try to make it sufficiently big so that we can see what's going on. Yeah, maybe we don't need origins here. We have open ball. That should be our x, and this should be our epsilon here, the radius. So everything here is inside our x, and we're saying this is open, so we don't have the boundaries, something like this. And now I'm taking an arbitrary y. So let's fix our arbitrary y here. What I want to prove is that there is some open ball centered at y inside the ball that we have. So this is what I want to prove. And the idea here is something like, what's the radius that we need to take? What's this radius here? Well, to compute that radius, what we can do is we know what this is. That's epsilon. We know what that is. That's the distance from x to y. So this radius should just be the difference. Let's try to write it. So here, we know this thing is epsilon. The entire thing is epsilon. And we know whatever we have here is the distance from x to y. So whatever remains is the difference, epsilon minus the distance. That should be our radius. And now let's write the proof. So let's take y in the open ball x, epsilon. What this means, that distance from x to y is smaller than epsilon. Well, we know that this difference here is positive. So we know that, let's take color, epsilon minus distance is going to be positive. And that could be our delta. That's going to be our delta. So let's take that as delta. Insert more space. So this is one valid delta. Anything smaller than this will also work. Because in other words, we're just making this ball here smaller. But that delta is good enough. So now we want to prove that's not for free. We want to claim for that delta, the ball centered at y, radius delta, is a subset of the ball center x, radius epsilon. Want to prove this claim. So how do we prove this? Well, element chasing. Let's take some arbitrary element in ball y delta. I want to show that's a distance at most epsilon from x. So let's compute the distance. We compute the distance from x to c. So your c is somewhere over here. I don't know, something like here. The idea is this distance, it's going to be at most this sum. So let's compute it. The distance is by the triangle inequality smaller than the distance from x to y plus the distance from y to z. And this is the triangle. Okay, so distance from x to y, it is what it is. But the distance from y to z, it's at most delta. And that's because our z is an element in ball of center y, radius delta. And now I can write what delta is. So this is just distance from x to y, but delta is epsilon minus the distance. And now this is exactly epsilon. So what we just proved is that the distance from x to c, it's at most epsilon. Or in other words, this c is in the ball that we want. And that proves our lemma, because c was an arbitrary element in this ball. Okay, any questions? See, there's a question in the chat. Oh, no, there's no question in the chat. Just previous one. Okay. Now with that lemma, we can go back to our proposition. So here's our proposition. We want to prove this collection of open balls serve as a basis for some topology. So now proof of proposition. And of course here, what we're going to do is we're going to use what we called proposition 4 in lecture 3. So proposition 3.4. Here we need to prove two conditions. So the first condition says that the entire space X is the union is covered by all the elements in our candidate for a basis. And this will be for free I mean, of course, this inclusion is always true, but the other one, if you take an arbitrary x here, then we can just include it in some open ball. Given an arbitrary x in x, we know that x is going to be an element in any ball centered at x of positive radius, say radius 1. So x is in one of these balls, which means it's also in the union. So that's not the complicated part. Complicated part here is the other one. So this other condition is you take two basic sets, you intersect them, and you take something on the intersection. Then you should be able to include the ball in the intersection. So the picture is something like this. The second condition, so let's say for the second condition, in proposition 3.4, we need to take two balls. First ball is here, second one is here. Maybe that's second one is here. You intersect, you take any point here, and you want to include a ball in the intersection. So I'm just going to use my lemma. So let's take two basic sets, then B x1 epsilon 1 and B x2 epsilon 2 in my B. And now I need to take an arbitrary element in the intersection. x1 epsilon 1 intersection B x2 epsilon 2. And the idea now is, well, using my lemma, because of this, since y is an element on the first one, because it belongs to the intersection, we know by the lemma there is some delta 1, let's call it, such that not only y, but the entire ball, center y of radius delta 1, is inside ball x1 epsilon 1. So here, if this is my ball x1 epsilon 1, I'm taking a ball for the first one. So could go outside the second one, but the important thing is it's going to be inside the first one. Maybe something like this. Probably need to change the center. So this is my delta 1. And now for the second, same argument. Since our y is also on the other ball, because it's in the intersection, x2 epsilon 2, there's probably some other delta that's going to work for that second ball. Y delta 2 now inside the other ball, x2 epsilon 2. Okay, so maybe something like this. Maybe that one is good enough. And now we can just take the smallest one. So if we take delta to be the minimum between delta 1 and delta 2, so whichever of these two is smaller, we take that one. In this case, the ball center y and radius delta is, well, since delta is smaller than delta 1, smaller than or equal to, this is going to be a subset of delta 1. But again, delta is smaller than or equal to delta 2, so it's also a subset of the second ball. And now the first one is a subset of x1 epsilon 1. The second one is a subset of x2 epsilon 2. And we're done. This is exactly what we wanted. And this proved our proposition. So in other words, we proved whenever you have a metric space, or whenever you have a metric on a set, then this business of taking open balls, that's going to give you a basis for some topology. So maybe, yeah, before we end the class, let me just note, I want to note something, because this is the most natural moment to say this. If we use the local description of our topology generated by basis, So this is what we call T of B, and we're denoting now by T sub D because it comes from the metric D. We have a local description for TD. So TD is going to be all subsets of X such that whenever you have a point on that subset, you can always include an entire ball. So there's some epsilon such that not only X, but entire ball is inside your U. So this is the metric topology. And yeah, let's stop here.